Assalamualaikum and good day to Prof and Azlina. So everyone, we are from group 2, which is for first and Rabahat. We're willing to share our heat SCD design. So in this team, we have Wong as our leader, Siti, Aisyah, Kishanraj A, and also me, Daniel. So in the table of content, we have our literature review until issues, posting, and also some recommendations. So for this part, for our process description, we know that heat exchanger are used to transfer heat without mixing them together. And then we need to cool our nitrogen and hydrogen gas. And also we use water as our coolant. So for our case study, we need to cool down our hot gases before it's enter ammonia converter unit. And for this project also, we are required to find our size of the heat exchanger, pressure drop, and also the heat transfer coefficient. For the hex description, we use 1 partial. Since 1 partials, we choose it due to its simplicity and also cleanliness issues. And also we have 2 tube passes. And then the type of shell and tube heat exchanger, we use floating head since it is the most versatile of it. And then for the methods we use, we put water in the tube since it have greater falling factors and mechanical cleaning are easier in the tube parts. And also we use copper as our piping material since it have one of the greatest thermal conductivity. For the design shape of hex, we have for the front end stationary head types, we use channel and removable cover. For the shell type, we use 1 part shell. And also for the rear end head types, we use pull-through floating head. So I will pass another part into Aisyah. Thank you.
So now I will present the schematic diagram for our floating head heat exchanger. As you know from our case study, we plan to do a process to cool the hydrogen and nitrogen gas by using water as our cooling medium. So this is the design that we proposed of floating head heat exchanger with 2 passes. Here I have labeled the components. This is our shell. We propose our shell to be stainless steel because of its corrosion resistant. The hydrogen and nitrogen gas will flow in the shell side. So here is the shell inlet and here is the shell outlet. Next is tubes where the cooling water will flow. So water will enter the tube inlet and flow inside the tubes and go out to the tube outlet. And we use copper as the tube material because of its best thermal conductivity. This is baffles. Baffles will create turbulence and enhance the heat transfer process. Next is the schematic diagram with the dimensions. For the length of the tubes, we choose it to be 9 meters. And the shell diameter, this is the diameter of the shell that we used. For the baffle spacing and number of tubes, this is the value that we have calculated. Next is tube dimensions. This is the outer and inner diameter that we used. For the tube layout, we use triangular pitch arrangement so that the bundle will have the greatest density. More tubes can be accommodated, allowing higher heat transfer. Here is the tube pitch, which is the center to center distance between the adjacent tubes. For the baffles, we use 25% baffle type. Then this is our prototype for floating head shell and tube heat exchanger. For this prototype, we use recyclable material. For the shell, we use mineral bottle. So here is the gas inlet and here is the gas outlet. And here is the tubes. So here is the water inlet and here is the water outlet. And then here is the tube sheet and at the back here is the floating tube sheet. And lastly, the red one here is the baffles. Next, I pass to Zhong Han for the calculation part.
All right, thank you Aisyah and Daniel for the introduction just now. Right now, let's have a look to the calculation part. Okay, so for our calculation, it mainly divides into 3 parts. First is the MTD method. Second is the tube and shell buffer selection. Then the last thing is the heat transfer coefficient. Okay, so for this MTD method, it mainly is to use to determine the required area of our design. Okay, so it's all starting from this problem statement. Okay, so for this MTD method, we have to focus on these 2 heat flow rate formula. Okay, first we identify the Q, okay, which is a heat flow rate by using the NC theta formula. Then second, we identify the U, okay, which is the heat transfer coefficient. Because right now we haven't gone into the details of calculation. For this heat transfer, we only can estimate it based on the provided table. Okay, so the third thing is the correction factor. Also, we get it from the table. Then the dt, delta T is the MTD. Okay, so we do the calculation. In the end, we get the area. Okay, so for this area, we would put another 10% of the margin to cope with the foul condition. Okay, so after we know the required area of our design, then we start to select the tube and shell that is suitable to our context. Okay, so first thing first, we find out the DO and DI, outer diameter and internal diameter of our tube. Then we identify the triangle pitch, our tube layout. Then here we make an assumption, which is our length of the tube is 9 meters. Why we put the 9 meters is because of this one is the maximum length for our floating head heat exchanger. Okay, so we know that the longer the length, then it will reduce the cost of our design. Okay, so after that, we find out the diameter of the shell, then we find out the number of tube. So here is all about our selection of the tube and shell and buffer. Okay, then the last thing is the heat transfer coefficient. For this heat transfer coefficient of the shell side, we use Bell-Delaware method. Okay, this method is the most reliable method at present for the shell side analysis. Okay, why it reliable is because it considers all the correction factor, for example, for the buffer cut, for the spacing, for buffer leakage effect, and so on and so forth. So in the end, we find out the shell side heat transfer coefficient is 1,580 here. Then for the tube side heat transfer coefficient is quite straightforward. Then we find out the transfer coefficient is here. Okay. Then after considering the fouling resistance and the effect of the wall, then we find out that the overall heat transfer coefficient is 251, which is quite close to the estimated. So which means that our estimated heat transfer coefficient is still acceptable because the deviation is only 5%. So after that, we try to find out the pressure drop. We know that we need to reduce the pressure drop, okay, for this to avoid the corrosion and so on and so forth. So for our shell side, we get in total 188 PSI. Actually, this one is quite high, but it's still logical because of the lower average density of the nitrogen and hydrogen result in the high pressure drop. Okay, after that, we identify the tube side pressure drop. This is a very good value because it's lower than the acceptable or permissible value, which is only 0.06 kilo over cm square. Okay, so we get only 0.06. So this is all about our calculation, and the details is already putting in the Excel file. Okay, so that's all from me. Thank you.
So we have two simulation graph here. The first one is heat transfer coefficient is a tube outside diameter, and it shows a decreased slope. And another graph is the heat exchanger area surface, this is the tube outside diameter, and it shows a positive slope. And for the safety precaution, we have 4 safety precautions, which is we need to avoid overpressure heat exchanger. During maintenance, we need to release the pressure from the heat exchanger and ensure the pressure gauge at 0 atm. And during operation, we need to carry on tube plugging due to build-up of fluids, and we need to do the startup and shutdown operation smoothly. And the 3 environmental issues here is we need to the removed materials during cleaning may contain carcinogenic or radioactive matters, and the releasing of the CO2 gases is also one of the environmental issues, and also the emission of anthropogenic emissions. And for the costing part, we need 2 materials actually, copper and stainless steel, and the stainless steel is for the shell and also for the baffles. And according to the for the price, we need for the copper we need almost 40 ringgit, and also for the stainless steel 27,540 ringgit. And for the stainless steel, as per the calculation, we need around 27.898 m square. So stainless steel we need around 34 pieces, and for the tube we need 1 kilogram of the tube. So since the copper we take the price at $780, since we need 1,226 tubes, and 1 unit of tube is 0.03265 ringgit. And for the recommendations part, so we need to replace the segmented baffles with helical baffles, which elevate heat transfer efficiency and decreases the pressure law. We can apply carbon capture technologies. Another recommendation is we can undergo the periodic cleaning in order to flush out the matters that decline the efficiency of heat exchanger. And also we can increase the pressure of nitrogen and hydrogen gas to reduce the pressure drop in the shell side. So that's all from our group, Thank you.